All right. So today we are going to actually start taking notes on new material for Unit 4. So far, what we've done is review. On Monday, we reviewed the Moving Man Lab, which was last unit, and then we also reviewed free fall, objects in free fall, which is connected to this unit. And today we're going to extend our understanding of vectors, which is something we've already learned to some degree, but we're going to extend that a bit. And then we're also going to talk about projectile motion, which is something new. And it will have a lot of overlap. We're going to see the same kinematics equations we've been using, but some new information as well. So I'm going to share the PowerPoint with you. And before we jump into the notes, just a couple of quick reminders and announcements. First, for the test, I have several students taking the test this afternoon, so I have not put the grades into the gradebook yet or made it visible for you yet. I did put in the comments on the gradebook your original grade and what your grade would be after the curve. And so if you haven't seen that, you could look at the grade book in the comments. You can't see your test, but you can see in the comments what your original grade and curved grade would be. I'll probably wait till the end of the weekend until I get everybody's grades done and I'll input it into Axis and then post it. Also, that gives you less time for those that didn't do very well. It gives you less time to have to look at the grade with the uncurved in there. And I know sometimes that freaks students and parents out when they see that uncurved grade in there and how it impacts their score. So I'll give you a little more days of reprieve before you have to worry about that. And then Monday, I should have everybody done by tomorrow evening. And so Monday, or tomorrow afternoon. So Monday, then we'll actually start doing corrections in class. And so that is the timing of that. And then next week, my plan is to give you a time on Wednesday, Thursday, and Friday next week to do a retake. So I'll give you 3 different choices. I have to look at the schedule next week and see what times it'll be. My assumption is it will probably be Wednesday morning and then Thursday and Friday afternoon to give you a few different options. So the morning time would be better for the international students, and then the afternoons probably typically better for more of the rest of you. So probably do that. But I'll give you that detail on Monday, which days and times, but that's the plan. And then the PhET activity, if you were able to get that done, you can just submit that on Axis by tonight. If you had some questions, there's going to be probably 20 to 30 minutes at the end of the class today for you to ask those questions and get some help, and also just to be working on it if you just didn't have time to finish it yet. And then the assignment today is worksheet 2. It is going to be on horizontally launched projectiles. So you can find that on Axis where you found worksheet 1 and where you found the PhET activity. There's a document and PDF form of it. And it will be what the second half of our notes is on today. So any questions about timelines or due dates or anything like that before we jump into today's notes? All right, let's get to it. So we're going to start first with vectors. So what is a vector? So someone unmute and remind me, what is a vector? I'm pretty forgetful, so I need reminders.
It's a variable or quantity that has both a direction and magnitude.
Good. So generally speaking, it's going to be something we measure. It wouldn't always have to be, could be given to us, but it's some numerical measurement, whether we've been given it or we've measured it ourselves, that has both direction and magnitude. And some examples, we've already learned a lot about velocity and displacement, but we will also be learning about force in the next unit. And so that'll be one coming soon to your virtual classroom. And we'll be studying that for most of the rest of the time between the end of this unit and the end of the semester. So those are 3 examples of vectors. 2 you're very familiar with and 1 that's right on the horizon. What's a scalar then? Somebody else, how is a scalar different than that?
It only has direction. I mean, it only has magnitude. It doesn't have direction.
Okay, good. So a scalar has magnitude only. We don't really care about direction. It's always going to be a positive value, because when we are working in physics, almost always, not always, but almost always, a sign, a plus or a minus, is almost always talking about not the size of the number, but instead the direction of the movement or the direction of the force. So signs in physics don't really generally have anything to do with magnitude. They have everything to do with direction. So a scalar is something that has a numerical value. That's what we mean by magnitude, numerical value, but no direction. The direction is irrelevant. And so temperature is one where it's just completely irrelevant. Speed is one where the direction might be relevant, but if we talk about speed or distance, those are scalar values, so the direction isn't given. And so sometimes speed could be considered the absolute value of the velocity if the object's traveling in a straight line. But if the object's traveling in any curving path or strange pattern, then the speed and velocity won't be the same, because the distance and displacement won't be the same. So occasionally the distance is the absolute value of displacement, and occasionally the speed is the absolute value of velocity. In fact, more than occasionally, often, but not always. We do have to remember that they technically are a little bit different, because distance is the path, whereas displacement is just straight from point A to point B. All right, so quick review there on what vectors and scalars are. Now we represent vectors. The rest is going to be mostly new, with just a little bit of review. This first part here is starting with some review. We've already been representing vectors as arrows, and we know that when we draw a vector as an arrow, the magnitude of the vector, the size of the number, is represented by how long the arrow is. So a very long arrow means it has a large value, and if it's a small arrow, it has a small value. But something new that we're going to be doing with vectors now is we're going to start talking about vectors that are traveling not just on the x-axis or just on the y-axis, but at some other angle. And if it's at some other angle, we need to be able to indicate what that angle is. So we will use the Greek symbol called theta. You can see it here in the sentence at the bottom and in the diagram. And we will typically measure, and when we get into the next unit, we'll start breaking this rule a little bit. But for now, we're going to typically measure the angle in the counterclockwise direction, just like you do in math class. So we start from the positive x-axis position, and we rotate back up counterclockwise to show what that angle is. So that's kind of the new twist that we're going to be thinking about, that vectors don't always have to be just on the x-axis or just on the y-axis. They can be at any angle. All right. Questions? Anybody need more time? All right, not seeing any waves, so I assume you're good to go. Now, most of what we're going to do today and in the coming weeks is going to involve either one or two vectors. Usually it'll involve one vectors that will break into parts. But we can have scenarios where there's multiple vectors. In the next unit, we're going to have many, 2, 3, 4, 5 vectors at a time. So I want to start to introduce the idea of when you have more than one vector, how do we add vectors? We did this a little bit when we were talking about displacement. We had examples like, if the object moves 30 miles to the east and then 20 miles to the west, what's the displacement? And it's 20 miles to the east. Like we can subtract them because they were both on the same east-west plane. Or we could do the same thing for something vertically, but they don't always have to be just in one plane. We're going to be talking about two-dimensional motion from now on. Not always, but often from now on. And so if we have two different vectors, like maybe this A vector is a plane flying through the air, and the B vector is the crosswind that's going to impact the flight of the plane. Well, we can put those vectors together in a method that we call tip to tail. We're just going to pick one as the first vector. In this case, I'll pick A as the first vector. And then we're going to move B to where the tip of A touches the tail of B. So that's why we call it tip to tail. Now, when you do line them up this way, tip to tail, the tip of A to the tail of B, you have to make sure that as you're kind of virtually moving this vector B across the table, that you do two things. You have to make sure that you keep it parallel so that you don't change the angle. And you also need to make sure that you don't change its length. So moving it straight across the paper, keeping its angle and keeping its length consistent. So when we add vectors, in this case, we can't literally just add them using simple arithmetic like we did before. We can't say, like that example before, 30 miles east and then 10 miles west gives us a displacement of 20. We have to add them geometrically. And so this vector addition is a graphical or geometric addition. We're even going to be incorporating trig into the process of adding these vectors together. All right, so it's not literally just A plus B because they're not going in the same plane. You have to add them geometrically. And we're going to talk about how to do that here in a second.
I have a question.
Yeah.
So A would be like the object's movement, and then B would be like some like other force acting on it. Is that what you said?
That would just be an example, a pretty common example. So if we do use that as the example, so here's the plane. The plane is flying along the path A, but the wind is blowing along the path B. So if the plane doesn't make any corrections, the plane's actually going to end up as if it traveled on path R. Does that make sense? If the pilot doesn't make any corrections, the plane's going to end up as if it was actually traveling on the path R here. We call that path R the resultant. And like I said, it's not literally the value of A plus the value of B. It's a vector addition. We have to add them geometrically. So if this is a right angle, we can just use Pythagorean theorem, or we can use some trig functions. If it's not a right angle, then we're going to have to use some other creative solutions. But the key being, it is going to be the third side of the triangle. It's not going to be literally A plus B in arithmetic. It's going to be A plus B as vectors. And we'll practice that, but I want to introduce the concept first. Before we practice it though, I want to make sure you understand that whenever we have two vectors, whatever they happen to be, it could be like a running back running one way and a defensive back tackling them at two different angles. So it could be all kinds of different things. But if we have two vectors to consider, this vector addition, you notice they put little arrows above the letters here to indicate that these are vectors. So we can't just literally add A to B. We have to add them as vectors. So we want to do the tip to tail method. If I choose A as my first vector and put B, its tail to the tip of A, I would just align them that way. And the resultant is just the third side of the triangle. So if the running back is running along path A and the defensive back is running along the path B and they collide, then in the end, they're going to end up over here somewhere, right? And so it's just showing us the combination of these two forces or movements or whatever we happen to be evaluating, what they would actually end up resulting in when we combine them. So just lining them up tip to tail. Now I chose to make A the first one and B the second one. And so the vector sum is the third side of the triangle, the resultant of that. But it doesn't have to be A first. It could be B first. So same two vectors. If I choose B first and then add A to it, the resultant is still just the third side of that triangle. And if you recognize the two triangles I've drawn, they're actually similar triangles. The resultant would be the same length and their internal angles would be the same angles. So it doesn't really matter which one we pick first. This is the commutative law at play for vector addition. Whether we start with A and add B tip to tail or start with B and add A tip to tail, both ways it's going to give us the same triangle in terms of having the same third side in magnitude and the same angles between them internally. So that is the commutative law of adding two vectors together and finding the third side, the resultant. Questions? So in the future, especially in the next unit, we're going to have more than just two forces. There could be 3 or 4 or 5 forces. And so not only is there a commutative law to adding them together as vectors, there's also what we would consider the associative law of adding vectors. So here we're going to look at adding 3 of them together. When you have more than 2, you can't just put them in any shape necessarily. You have to take 2 of them and find the resultant. So you'd make a triangle out of 2 of them. And then you add the third one to that resultant. Okay, and then if there was more, you would find the resultant of the first resultant and the third one, then find that resultant and add a fourth, and you just have, so you start with 2, make a triangle, and you just keep adding them on one by one to the resultant. So I'll walk you through how this looks. So the associative law, if you think about what it means in math, it means we can associate 2 and 3 and then add 1, or we can associate 1 and 2 and then add 3. Or we could associate 1 and 3 and then add 2. In other words, we can put the parentheses around any pairs and we can put them together in any pattern. But we do have to associate them if there's more than 2. So let's say we decided to put 1 and 2 together first. If we put 1 and 2 together first, here's 1 and here is 2. And then this is the resultant, the vector sum of 1 plus 2. Then from that vector sum, we're going to add the third one and find our final resultant. Okay, so you put 2 together, make your triangle, getting that third side, and then you're going to put the third vector on that third side of the triangle you created, and then make a new triangle. And if you had another one, you would put the fourth one on this one, and then make a new triangle. You just keep adding them on one at a time after that and making a new triangle, new triangle, new triangle, starting with the resultant of the previous ones. But this is if we started with 1 and 2 to make our first triangle, then added 3. If we started with 2 and 3 and then added 1, we end up getting the same result. Here's 2 and 3, and we get the resultant. And we put 1 on there, and it doesn't matter, like we saw in the previous one, it doesn't matter which one we do first. So we can put 1 on the tip to tail either way. So it makes sense to put it this way. So we've got it this way, and we got our new resultant. You see this resultant is the same value at the same angle. And if we kept adding more and more on, we would just keep getting the same results. So it doesn't matter which order we group them in, and it doesn't matter which order we add them in. Commutative properties and associative properties apply to vector addition. Now this, like I said, this commutative and associative property is more of a preview of what you need to understand for the next unit, Unit 5. Because we're talking about vectors today, I wanted to start to introduce it, and then we'll spiral back to it later when we get to Unit 5. Any questions about commutative or associative law of vector addition? All right, well, let's practice it. So let's say we have some vectors that we're going to try to resolve. We're going to try to find the resultant. So we have this person walking, and this person chooses to walk 6 meters south and then 9 meters east. Okay. So the distance they've walked is 15 meters, but the displacement is not 15 meters, right? The displacement is straight from point A to point C. So we need to draw a line from point A to point C, and that third side of the triangle is our resultant. But this is a right triangle because they were going south and then they went east. So because it's a right triangle, how can we find the length of that resultant?
Pythagorean theorem.
Pythagorean theorem. All right, so we know that we can add the legs squared, and that will equal the hypotenuse squared. The sum of the legs squared equals the hypotenuse squared. And we know the two legs are 6 and 9, so we can add those together, take the square root. And the third leg of this triangle, the resultant displacement, is actually 10.8 meters. So this person walked 15 meters, but they are 10.8 meters away from where they started. Questions? Hopefully the concepts of distance and displacement are coming back and kind of being refreshed and not too difficult, but now we're just not all on the same axis. Now we're looking at angles, so we have to use things like Pythagorean's theorem to solve it. All right. Now, what if you aren't given more than one vector? What if you're only given a single vector, but it's at an angle? Well, there's another thing we can do with vectors that helps us solve problems when they're moving in 2 dimensions. So if this car is moving northeast, well, that means in some of its motion, it's easterly, in some of it, it's northerly. So it has both a transition in the northern direction and a transition in the eastern direction. So we can break down that movement of the car that's actually traveling along that one vector. We can actually break it down into its horizontal and its vertical components. So here we're supposing the car is moving straight from start to finish, right along this dark blue line. So that is its actual vector. But we could think about the fact that because it moved in a northeastern direction, there is a certain amount of x displacement and a certain amount of y displacement, or an x distance and y distance, depending on how you want to phrase it. And it's also true, the car could have finished in this same spot by traveling east first, and then turning 90 degrees and then traveling north. and it would have ended up in the same place. Now, it would have traveled a greater distance, but its displacement would have been the same. Technically, we could get from start to finish in any route, right? We could drive all over the place if the roads weren't binding us. We could drive some sort of circle route or curvy route or all kinds of turns. But we want to be strategic in the way that we break down the actual vector, and we want to make it always into a horizontal and a vertical vector. And here's why. We're going to kind of dig into this a little more. These X and Y vector components, we call them components because they are the X and the Y parts that make up the overall displacement. And so we are going to strategically always make one horizontal and always make one vertical so that we can say, well, one is along the X axis and one is along the Y axis. It makes things simpler. And the other feature that makes it simpler, if we always break it down into horizontal and vertical, the X and the Y are always perpendicular to each other. And because they're perpendicular to each other, that's going to give us some other advantages. So as it says here, the components that we use, we're going to place them not just anywhere, but we want to place it where it's going to be convenient to help us do some calculations, right? We could use it in any way that makes it easier for us, but making it at 90 degrees is the easiest. It's the most helpful. So that's what we're always going to do, is make it at 90 degrees. So like it says here, another feature when we set this up is the X and the Y. We don't generally just want to make them whatever. We want to make sure they're perpendicular. If they're perpendicular, that provides a nice asset for us in terms of problem solving. Just like we saw in the previous example, we could use Pythagorean theorem because it's a right triangle. If we know the hypotenuse, if we can find one other side, then we could find the third side as well using Pythagorean theorem. If we don't know either side, we only know the hypotenuse, but we know an angle, what could we use to find the sides if we only know the hypotenuse and an angle?
Sine, cosine, and tangent.
Yeah.
Sine, cosine, and tangent. Yeah, we can use our trig functions. Okay, we're going to review that. For those of you that have had a lot of experience with trig, this will be a very simple review for you, just kind of refresh your memory. For those that have had little experience with it, hopefully you can take some notes and make sure you really understand it before we're done. So first we started with, what if we have two vectors or three vectors? How can we arrange them? We found we can arrange them in all kinds of ways. Now we're saying, well, what if they only give you one? And that's not enough information. What if you need to find some other things about it? Well, if it's at an angle and you know that angle, you can use trig and find those two sides of an X component and a Y component. And we're going to see how that's helpful in projectile motion here in a little bit. So for trig, just as we can resolve a vector from its components, we can also, so the first thing we did was resolve a vector from its components, right? We had the 6 meters and the 9 meters, and we found that resultant vector. We can also do the opposite. We can start with the vector and find its components using trig. So the steps you want to take are, first you want to draw a diagram that creates a triangle with the one vector that was given. And then you're going to sketch in the horizontal and vertical components that do meet in a perpendicular fashion to create that right triangle. And then we're going to use trig to work out what the X component and the Y component are, what the horizontal side and the vertical side values are. As long as we know one side and one angle of a right triangle, then we can use the trig. Now, in math class, you're generally taught not just this SOHCAHTOA pattern, you're taught wisely so, what is sine, what is cosine, what is tangent, how does it fit, connecting to the unit circle, all of that good stuff. And that's super important to help you understand the baseline of what it means and why we use it. But in this class, I'm fine with you using SOHCAHTOA because I'm hoping you're learning all that background solid information in math, and that here we can just very quickly apply it. If you have to stop and think about the background for sine and cosine and tangent in physics, then you're not going to have time to get the problems done because you're always pinched for time on a test or an exam in physics. So I'm fine with you thinking through the SOHCAHTOA abbreviation. And if you haven't heard that, it's just SOH means sine is opposite over hypotenuse. CAH is cosine is adjacent over hypotenuse. And TOA is tangent is opposite over adjacent. So it's just an acronym to help you remember the pattern of what sine, cosine, and tangent stand for. All right, so with this hypotenuse that was given, this vector of 15 meters at an angle of 20 degrees from the horizontal, we've created our right triangle. And if we want to find the opposite side, we're going to use the sine function because we're looking for the opposite and we know the hypotenuse. If we want to find the adjacent side, we're going to use cosine because that would compare the adjacent to the known hypotenuse. Until we find one of these two sides, we can't really use the tangent function yet because we don't know either the opposite or adjacent when we first start. So we want to start with one of these two, but eventually we could use this as well. So in this instance, if we want to find the opposite side first, if we want to find that vertical side, we would use sine, and it would be sine of 20 because that's the angle equals opposite. So this red vector, this vertical vector is opposite on that triangle. It's the opposite side of the triangle from that angle over the hypotenuse, which is the 15 meters. If we wanted to find the horizontal, the green one, we would use cosine because that is adjacent, which would be this horizontal over the hypotenuse, the 15. So that's a quick review of how we apply sine, cosine, and tangent. So let's practice one. If we have a displacement vector with a magnitude of 175 meters and it points at an angle of 50 degrees relative to the x-axis, find the x and y components. We've got a 175 meter, basically hypotenuse. We're going to recognize it's at a 50-degree angle to the x-axis. We're going to draw an x component and a y component that are perpendicular to each other and close that resultant hypotenuse in as a right triangle, and then use trig to find the x and y components. So I want you to go ahead and try. For those of you that are comfortable with trig, you should be able to do this pretty quickly. For those of you that are not as comfortable, hopefully you can wrestle with it a little bit and see if you can come up with it. Solve these x and y components and put them in the chat when you're done. If you're struggling with how to get started, I'll give you a hint. Draw it first. In the chat, you can just put x equals whatever you come up with and y equals whatever you come up with.
Do we round to 3 significant figures?
Sure. Give you another 30 seconds to keep processing it for those still working. All right, for those that have put the answer in the chat, you're all coming up with the same results. Let's make sure they make sense. What would this angle have to be so that the X and Y sides were the same?
45.
45 degrees. Since it's 50, this side has to be longer than that side, right? So the Y should be a larger value than the X. And everybody that I've seen type it in has a larger value for Y than X. All right, so let's break this down and show you how to solve it. So we know sine is opposite over adjacent. So sine of the angle is going to be Y, or sorry, opposite over hypotenuse. So it's going to be Y over R. And if we want to solve for Y, which is what we're trying to find, that would be multiplying both sides by R. So R times the sine of the angle. We know R is 175, that was given. We know the angle is 50. And so if we solve that, we should get 134 meters, which is what most of you were finding. For the second part, we're going to use cosine because we're trying to find the X, and compared to 50, the X is adjacent to it, it's beside it. The Y is opposite the 50, the X is beside the 50. Adjacent means beside. So we're going to use cosine. Cosine is adjacent over hypotenuse. The adjacent is the X, the hypotenuse is the R. So cosine of theta would be X over R. To solve for the X value, which is what we're trying to find, we multiply both sides by R, so we get X would be R times cosine theta. Well, again, R was given as 175, and the theta, the angle, was given as 50. And so we find that the distance, or the component length for X, is 112 meters. Questions? All right, now what would this angle be up here in this triangle, this alpha?
40 degrees.
40, yeah, these have to add up to 180, so that's going to be 40 degrees. Could we solve this using that 40-degree angle?
Yeah.
Yeah, we can use whatever angle we want, not the 90, but we can use the 40 and the 50. And so we could also recognize that alpha has to be 40. And just so you know, if you're not as comfortable with trig, you can use either angle, you'll get the same result. So if I chose to use this 40, I would take the cosine to find Y, because Y is adjacent to the alpha. Y is beside the alpha. X is opposite. So I just have to flip and use cosine to find the Y and use sine to find the X, but I'll get the same results. So it doesn't matter which of those angles you use. You just have to recognize that Y is opposite of 50, but Y is adjacent to 40. So you have to make sure you're using the correct function based on those positions. All right, now we're going to dig into projectile motion for the last bit of our notes here, the second half, a little less than half probably time-wise, but projectile motion is motion through the air without constant propulsion. So like shooting a basketball. Once you've shot the ball, there's no motor, there's no power being inputted to the ball while the ball's in the air. So once the ball's left the fingers of the shooter, we would say the ball is a projectile. It's just flying through the air. The only thing affecting it is gravity and air resistance, and we're going to always ignore air resistance, or almost always ignore air resistance. A ski jumper, they may get themselves a push to get started, and they're going down the ramp, and the ramp is supporting them, but once they launch off the ramp and they're in the air, they are themselves a projectile. Once they're in the air, the only thing that's guiding their motion is gravity and air resistance. And like I said, we're going to typically ignore air resistance. Another example would be hitting a golf ball. After the ball's been hit and it's flying through the air, it's a projectile. There's nothing driving the ball anymore other than its own inertia. So it's got inertia because it's in motion. It's going to stay in motion after it's been hit. The only thing affecting its motion is going to be gravity and air resistance. And you can probably say it with me, hopefully by now, we're normally going to ignore air resistance. Okay. In fact, if you look at the AP curriculum equation sheet, on the side that's only half full, there's a little box with several statements, 4 or 5 statements. And one of them says, unless specified otherwise, always ignore air resistance. So it says it right on the equation sheet. So keep that in mind. All right, here's a way we could define it. So if you prefer to have a more word definition, projectile motion refers to the 2D motion, two-dimensional motion of an object that is given an initial velocity. So something had to put it in motion and then projected into the air at some angle. Now today, the angle that we're going to project things at is 0. We're always going to just launch them horizontally for today. And then next week, we'll look at launching them at other angles. The only force acting on the object is gravity because we're ignoring air resistance. And therefore, it follows a parabolic path. And that path will be determined by two things, both the initial velocity that it was launched with and the gravitational acceleration. Now, the gravitational acceleration is not going to change. It's virtually constant near the surface of the Earth. So that aspect is going to be constant. But the initial velocity depends on what it was. So if it's a baseball getting hit, it depends on how hard it was hit. If it's a football being thrown, it depends on how hard it was thrown. So that initial velocity is going to impact basically how wide or how narrow that shape of the parabola is. The gravitational acceleration is constant, so it's not, that won't really impact it. It does impact it, but it doesn't change from problem to problem. All right, so that is a way to define what we mean when we say projectile motion. And you'll see some books even call it parabolic motion. Most of the time it's called projectile, but because the path is parabolic, you'll see that sometimes interchanged. So let's dig into what this means. So today we're only going to work on launching things horizontally. So like a ball rolling off a table. If there was no gravity, the ball would just keep flying straight. If there was no such thing as gravity, right? It would just keep flying straight. And because we're ignoring air resistance, it would never slow down. It would just keep going forever. That's actually Newton's first law, which we'll learn in the next unit. If it were just dropped, if it didn't have any horizontal movement, if it was just dropped, it would just be in free fall and it would fall straight down with an acceleration of negative 9.8 meters per second squared. But in this case, it's neither and both of those things. It's not just in free fall and it's not just moving horizontally, it's got both. And so just like we could combine those vectors together to find the third side of the triangle, we can combine these two aspects of this object's motion into the resultant vectors, the third side of the triangle. So you can see it has horizontal motion and vertical motion, and right here, those combine to give me the resulting motion. At this point, this red dot is moving at this angle, but it has a horizontal component to its velocity, and it has a vertical component to its velocity. At this point, the purple ball is now moving at this angle. The horizontal component hasn't changed, but the vertical velocity has because gravity is causing it to speed up. Gravity is causing it to accelerate. The bluish purple ball is moving still horizontally the same value, but vertically now even faster because it keeps being accelerated by gravity. So its actual angle is now this angle. And then in the green position, it's still moving the same horizontally, but now it's moving even faster vertically. So now it's moving at this angle. So the angle the ball is moving at is constantly changing, and the velocity the ball is moving at is constantly changing, because even though the horizontal component is consistent, the vertical is accelerating, and you have to combine both of them together. So we keep getting a different triangle at every instant, and therefore a different hypotenuse at every instant. Another way to look at it is to look at just the components. If we fired a cannon off a cliff in a horizontal direction, horizontally, if it was fired at 20 meters per second, it would continue to travel horizontally at 20 meters per second until it hits the ground. But vertically, initially it has 0 vertical velocity. Right when it's launched, it hasn't had a chance to start falling yet. So it has no vertical velocity right at that instant. But 1 second later, it's going to be going negative 9.8. And 2 seconds later, it's going to be going negative 19.6. And 3 seconds later, it's going to be going another negative 9.8 added on. So you can see horizontally, the component is constant, and vertically, the component keeps increasing because of the acceleration due to gravity. So you can think about it as a sequence of triangles, or you can just think about it as the x and y components of the velocity. All right, let's keep digging into this more and more. There's a law called the law of compound motion. And the law of compound motion says this: when an object is moving in multiple directions, both x and y, the motion in one dimension has no effect on the motion in the other dimension. So that acceleration due to gravity in the vertical has no effect on the horizontal. And the horizontal constant velocity has no impact on the vertical. They can be completely separated from each other. In the animation at the bottom, you can see something is being launched off a cliff, this time not horizontally, but at some other angle. And you can see the data down here at the bottom of the animation. Time is passing and the vertical velocity is changing, but the horizontal velocity is not. So even though the vertical velocity is changing, the horizontal velocity is unimpacted. And even though the horizontal velocity stays constant, the vertical velocity still can change. And you can see as it gets launched, it gets less. It goes 60, 50, 40, 30, all the way to 0 at the peak in terms of the vertical velocity. And then it increases in magnitude in the negative direction after it reaches the peak. So it's decreasing till it reaches the peak vertically and then increasing in the negative direction after. But the path is actually parabolic because it has this constant horizontal velocity as well. One last view of it. Well, this kind of set of pictures is going to help you sort of sum it all up, hopefully. If we have an object that's launched, and today, again, we're going to focus on horizontal. If this is launched horizontally, it's actually going to travel in a parabola because of gravity. So if we think about that initial velocity, it's going to cause its movement to travel like that. And if we looked at it as like with a strobe camera, we could see that at every instant, it's going to be in a different position following along that parabolic path. Now, if we think about the two components, though, of the velocity, the horizontal component stays constant. The distance between these yellow ones across the top stays the same. But the vertical component keeps increasing because of gravity. If we put a grid on it, you can see it even better. Horizontally, the divisions on the grid stay the same distance apart. But vertically, the divisions on the grid increase because the object is accelerating in the vertical plane. So velocity overall is changing. And if the velocity is changing, there is an acceleration. That's what acceleration means, right? A change in velocity over time. So the velocity is changing, not horizontally, but it is vertically. Therefore, the resultant velocity is also changing. The hypotenuse is changing. If we look horizontally again and draw the vectors on, all the horizontal vectors are constant. We're ignoring air resistance. Gravity doesn't impact things horizontally. And so there's no force. There's nothing causing it to slow down or speed up horizontally. It just stays the same the whole time horizontally. But vertically, it does increase. And because the hypotenuse is the combination of these two, the hypotenuse is also going to increase. And remember, the hypotenuse is actually the real velocity of the ball. The ball has a component that's horizontal and a component that's vertical, but its actual motion is along these diagonal lines, which is the resultant velocity of the ball. So you can see initially it only has horizontal velocity at the very beginning instant, but gravity starts to pull it down. And so a little bit later it has both, which gives it an angle. And then the vertical increase is giving it a greater angle, and then a greater angle, and a greater angle. And it just keeps increasing both in its angle from the horizontal and in its magnitude until it finally hits the ground. The acceleration, like we said, comes from the vertical component of the velocity, and that is accelerated because of gravity constantly and downward. And so in our kinematics equations, we can substitute A with G, because the only acceleration impacting it is the vertical acceleration of gravity at negative 9.8 meters per second squared. And you can still use the 10. You don't have to use the 9.8. You can still use the 10. So hopefully that helps sum it up for you. But here's a couple more facts that I want to make sure you understand. Not only do we know all of these things, you probably have all of this in your notes already. We've said all of these things and they've been on the previous slide, but now we're just trying to sum it all up with this one example. But there's a couple other things we can determine and conclude as we think about this example. One is that the horizontal and vertical motions are independent of each other. That's the law we talked about, the law of compound motion. We know that the motions share the same elapsed time, and this is critical. The amount of time that it's falling is the same amount of time it's moving horizontal. And that fact that the elapsed time both horizontally and vertically is the same is what helps us solve projectile motion problems. The horizontal velocity would just be the same as its original. So whatever its horizontal velocity was initially, it's the same at any given point in time. And the horizontal distance that it travels is going to be that that horizontal velocity multiplied by the time, because there is no horizontal acceleration. Since there's no horizontal acceleration, it's just distance equals rate times time. That is not true vertically, though. Vertically, there is an acceleration. So the vertical velocity will be g times t, however long it's been falling, multiplied by the acceleration due to gravity. And the vertical distance that it travels will be 1/2 gt squared. Now, if it's launched horizontally, like we're focusing on today, we don't need the rest of this equation. You hopefully recognize this is part of the second kinematics equation we learned. It's just missing the VOT part. But we can drop out the VOT part because the initial vertical velocity was 0. So it simplifies down to just 1/2 gt squared. Oops. So that is the conclusion of that example. Let me sum it up in a nice little table here so you can see it all together. I don't know if any of you take screenshots, but this might be a good screenshot if you like to take screenshots during the notes. Horizontally speaking, there's no acceleration. So whatever the whatever the horizontal velocity was initially, that's what it will be at any given point in time until it hits the ground. The displacement has no acceleration, so it's a simple distance equals rate times time. We can always use distance equals rate times time when there is no acceleration. You cannot use that formula if there is an acceleration, but horizontally speaking, there is no acceleration. And so we're going to separate in our brains the horizontal and the vertical. We're going to calculate those two things separately. Vertically speaking, there is an acceleration. It's due to gravity. Therefore, the vertical velocity will be ever changing based on that acceleration, and the displacement will be based on the second kinematics equation. But for objects launched straight horizontally, we drop out this VOT part because vertically speaking, when it's first launched, before it has a chance to fall, its initial vertical velocity will be 0. So this VOT for horizontally launched projectiles ends up canceling out. Questions? That's the end of the notes. We're just going to do a practice problem together to wrap it up. All right. So hopefully, if you were missing some things in the PhET, things that didn't quite make sense about the vectors or about the motion, hopefully this will help you wrap up that PhET activity and get that completed and turned in tonight. Then the assignment today for Monday is worksheet 2, which you can find on Axis in topics for Unit 4. And it is on horizontally launched projectiles. So I want to do one practice problem together with you here in the last 4 or 5 minutes to make sure you know how to set it up, how to think it through, so that you'll be better off on the worksheet 2. All right, so let's look at an example problem. The following figure shows an airplane moving horizontally with a constant velocity of 115 meters per second at an altitude of 1,050 meters. The plane releases a care package that falls to the ground along a curved trajectory. Ignoring air resistance, we are going to determine, number 1, the time required for the package to hit the ground, and then number 2, how far east the package travels during its fall. Most often, we will find the time using the vertical information and then plug that into the horizontal information to figure out how far it goes side to side. Occasionally, though, they mix it up and they give you different information. So just recognize you might not always do the pattern the same order, but the connecting thing is the time, because the vertical and horizontal are always connected with time. So this is the question. Here's the image. We've got a plane flying along straight path, 115 meters per second, and it drops a package. That package has a 115 meters per second velocity when it's released from the plane, because that's how fast the plane was going. And it will continue to have a 115 meter per second horizontal velocity until it hits the ground, because we're ignoring air resistance. Vertically, right when it's released, the instant it's released, it hasn't had a chance to accelerate yet, so its vertical velocity initially is 0. But an instant later, it's going to be traveling at some velocity because gravity is going to accelerate it down. So its vertical velocity will be increasing over time. We've labeled all aspects. Now notice that they have labeled positive as upward. So that means our acceleration is negative 9.8 and our displacement is negative 1,050 meters. Okay, they've labeled what they're defining as positive right over here. Any questions about the setup? All right, so horizontally, all we know is the speed. We don't know the time and we don't know the distance. So there's only one thing we know horizontally, so we can't really start there. Vertically, we know the initial vertical speed was 0, because right when it was dropped, it would have a 0 initial velocity. We know the acceleration is negative 9.8 because of gravity. And we know how far it's going to fall because the plane was 1,050 meters high. So we know 3 things vertically. So we should start there because we know more information about the vertical. Vertically speaking, if we use this equation with this part canceling out because the initial velocity is 0, the distance is this 1,050. The g is negative 9.8. Since the 1,050 is negative and the 9.8 are negative, those negatives cancel. So we would have 1,050 meters as our displacement, 9.8 as our acceleration, the 1/2 as a constant. We're going to multiply both sides by 2 to get rid of the half, divide both sides by 9.8, and then take the square root to solve for t. And the time would be, with 2 sig figs, 15 seconds. And you could technically leave it at 3. If you use 9.8 and you want to consider that in sig figs, that's okay. College Board accepts that logic, and you can make it 15. College Board also knows a lot of teachers say you should ignore the sig figs of the 9.8 and only think about the given values. So if you do that and you had 14.6, that's okay as well. Now we know the time, and the amount of time it's falling vertically is the same as the amount of time it's moving horizontally. So horizontally, we know the speed was 115, and now we know it was falling for 15 seconds. So horizontally, distance equals rate times time. There is no acceleration for horizontal movement, so we don't have to use the original kinematics equations. We can just use the simple distance equals rate times time. The velocity is 115, and the time is 15 seconds. So it would travel 1,700 meters. And that is how you solve a horizontally launched projectile problem. You have to break it down into the vertical and the horizontal and recognize time is the one variable that overlaps between the two. Also recognizing that horizontally, there is no acceleration. So you have a very simple distance equals rate times time. But vertically, there is an acceleration. So we have to use the kinematics equations. Any questions? All right. So that is the end of the lesson for today. If you have questions about the PhET or about anything else, we got about 25 minutes of class time left. You're welcome to stick around and ask questions. I'll keep the Zoom running the whole time. So even if you leave and then you realize you have a question, you can come back. I'll keep the Zoom running till 11:25, the normal dismissal time. But if you have no questions, at this point, you can be dismissed and you can work on getting the PhET done, or you can work on worksheet 2, whatever it is that you need to work on. But I'll be here if you have questions. If I don't see you in the next 25 minutes, have a great rest of your day. And if I don't see you tomorrow, have a great weekend.
Thank you.
You're
Thank
welcome.
you.
Thank you.
You're welcome.
Thank you.
You're welcome.
I have a question about